All right, everyone, get ready, because today we are taking a deep dive into a paper that's really making a splash in the AI world. It's called Thinking Slow, Fast: Scaling Inference Compute with Distilled Reasoners. And this one really caught my eye because it's tackling a problem that I think we all kind of struggle with. How can we make those large language models reason better without needing, a server farm the size of a small country?
Oh, that's a great question. Yeah, it's the million-dollar question for sure. And what's really fascinating to me here is how these authors are kind of exploring that using these subquadratic architectures like Mamba. These are known for being really efficient, especially when we're talking about long sequences and large batches, which is, perfect for those of us who don't have access to unlimited computing power.
You're so right. It's like they're really trying to find that perfect balance between, how big the model is and how well it can actually reason. And they didn't just stop at exploring Mamba. They actually went a step further. They took the knowledge from these huge pre-trained transformers and distilled it into these smaller, more compact Mamba models. And they created two different types: pure Mamba models, which they call Lumba, and then these kind of hybrid Mamba transformer models. Those are called Mamba and Llama.
Exactly. And this brings us to like a super important question, right? Can these smaller distilled models actually keep up with their big brothers, the transformer models? And to figure that out, the researchers put them through their paces. They really focused on mathematical reasoning tasks. So they used data sets like math and GSM-8K.
And this is where things get really, really interesting. They found that given a certain amount of time, those distilled models, those Mamba and Llama models, they could actually do better than the bigger transformers on these math problems.
Yeah, it's a little bit counterintuitive, right? You'd think bigger is always better, but the secret weapon here is speed. Subquadratic architectures are inherently much faster at generating responses. So what that means is they can come up with a lot more chains of thought, or we call them Kutis, within the same amount of time.
Kutis. Now, just in case some folks haven't come across this term before, Kutis are basically like the model's way of showing its work as it's trying to solve a problem.
Yeah, exactly. It's like model thinking out loud, as it's working through the problem.
So even though these distilled models might be a tiny bit slower on each individual step, their overall speed lets them explore way more possibilities, which gives them a better shot at finding the right answer in the end.
It's like the tortoise and the hare, wouldn't you say?
Oh, I love that.
Yeah, the Mamba models are like the tortoise. They might be slower at each step, but they're consistent and thorough.
Exactly, and they get to the finish line first. It just shows you there's more than one way to solve a problem. Now, the paper also digs into something really interesting, this whole idea of coverage versus accuracy. They discovered that those smaller models are surprisingly good at coming up with the right answer, what they call coverage. But the bigger models are better at finding that answer in a limited number of tries, which is the accuracy part.
Yeah, that's a really important distinction, and it has big implications for how we think about building and training our models. Like if you're working on a task where it's easy to check if an answer is right, like coding or writing proofs, well, then coverage might be even more important than just raw accuracy.
That makes total sense. If you can easily check if the answer is good, it's probably better to have a model that can generate tons of possible solutions quickly, even if it doesn't always hit the bullseye on the first try.
Absolutely.
Now, another really exciting thing they found was the effect of supervised fine-tuning, or SFT, on these distilled models. So it's like you take these already super efficient models and you give them this specialized training regimen tailored to a specific task.
Yeah, it's like giving them a crash course, a boot camp.
Exactly.
And the results are pretty impressive. After SFT, these Mamba models become even tougher competitors against those massive transformers. They show a huge jump in both coverage and accuracy.
So we've got these distilled models. They're fast, they're efficient, and they're surprisingly accurate. But how do they actually stack up in a head-to-head speed test? The paper compares the inference times of these models against those larger transformer counterparts.
Right, and they specifically looked at the Llama 3.2 architecture, so the 1B and 3B parameter versions. They used some of the latest tricks for speed, like Flash Attention 2 and Torch Compile for Llama and the standard Mamba implementation for the distilled models. They focused on generating 512 tokens from a 512 token prompt, which is, a pretty standard task.
And the results are pretty impressive. On a single NVIDIA H100 GPU, which is, a pretty powerful GPU, those distilled models were up to 3.7 times faster than the Llama 1D baseline. And get this, 4.2 times faster than the Llama 3B baseline.
Yeah, it's a pretty significant speed advantage, but, speed isn't everything.
Yeah.
We also need to see how this translates to actual performance on those tricky reasoning tasks. So to really test them out, they benchmark the teacher models. Those are the Llama 3.2, 1B Instruct, and 3B Instruct against their Distilled Mamba students. And they use two very well-known mathematical reasoning datasets, a 500-problem subset of math and a random 500-sample subset of GSM-8K.
And to make sure everything was fair, they used a bunch of different sampling techniques and temperatures, to level the playing field between the models. And for the process reward model, they used a Llama 3.1 8B Instruct model trained on Mistral-generated data. This was all about pushing those models to their limits and really seeing how they handle those complex mathematical problems.
Yeah, remember how we were talking about smaller models being really good at coverage? Well, that really came through here. When they looked at coverage as a function of time, the distilled models were in a league of their own. They reached the same level of coverage as their transformer teachers, but they did it in almost half the time.
So not only are they faster, but they're just as good at finding the right answer.
Now, there was a little bit of a dip in accuracy compared to the teacher models when using those traditional accuracy metrics. But remember, we're talking about specific time budgets here. And in that context, those faster generation times make a huge difference.
Absolutely. The distilled models could just churn out so many more completions in that same time frame that they actually got a better accuracy to time ratio for most budgets.
And what I think is really interesting is that those larger distilled models, the Mamba Llama 3B and Llama 4B, they actually outperformed the smaller Llama 1B baseline in both coverage and accuracy. And they did that all while being significantly faster.
So it's not always about going bigger, and faster doesn't always mean less accurate. This research really makes us think differently about how we design and use those language models.
It really highlights the potential of these subquadratic architectures and how efficient they can be.
Yeah, we can get really impressive results with models that are, a bit leaner in terms of parameters. And I think that this whole idea of coverage versus accuracy is a really important insight. The paper goes into even more detail about this, and the findings are pretty significant, especially if you're working on tasks where checking the answer is pretty straightforward.
Absolutely. What we see is that while smaller models might not nail the right answer on their first try, they're really good at finding the correct answer within a set of possible solutions.
Right. It's like they can think outside the box more and come up with more creative solutions, even if it takes them, a few extra steps to get there.
Yeah. And like we talked about before, in those cases like coding or proofs where you can easily check if an answer works, that ability to explore more broadly becomes super valuable.
For sure. It makes sense. Now, the paper doesn't just present these findings and stop there. They actually went on to look for ways to make these distilled models even better. And that's where supervised fine-tuning, or SFT, comes in.
Yeah, SFT is this powerful technique where you fine-tune a model on a labeled data set that's really specific to the task you're trying to improve. So in this case, they used a massive data set, 8 billion tokens from the OpenMath Instruct 2 dataset to fine-tune the Mamba and Llama models.
And the results were pretty impressive.
Well, yeah. After that SFT boost, those Mamba and Llama models showed a huge improvement in both coverage and accuracy. In some cases, they even did better than the original Llama models.
So it really proves that distillation gives you a really solid base, but, that targeted fine-tuning can really unlock the full potential of these models. You get this awesome combo of efficiency and accuracy. Now, I know our audience is probably wondering about the nitty-gritty details of how this distillation magic actually works. The paper outlines two main approaches, one for those pure Mamba models, the Llama models, and then another one for the hybrid Mamba transformer models, the Mamba and Llama models.
Right, so for those Llama models, they used a modified version of a distillation process called MOHawk. It's got 3 main stages, matrix orientation, hidden state alignment, and then weight transfer and knowledge distillation.
Okay, let's break that down a bit. So matrix orientation basically means you're making sure that the internal workings of the Mamba model line up with the larger transformer model. It's like teaching them to speak the same mathematical language, so to speak.
Right, and then there's hidden state alignment, where you're trying to match the output of each layer in that smaller Mamba model to the corresponding layer in the bigger transformer model. It's like making sure that each step in the student's thinking process mirrors the teacher's process.
I got it. And then finally, there's weight transfer and knowledge distillation, where you take any leftover parameters from the teacher model and you transfer them over to the student model. It's like giving the student a head start by using the knowledge that's already baked into the teacher.
Exactly. Now, for those hybrid Mamba and Llama models, they took a slightly different route. They modified a technique that was specifically designed for distilling knowledge into these kind of hybrid architectures. This approach is all about reusing weights from the attention layers of the transformer teacher.
So it's like giving that Mamba and Llama model a boost by building on top of the existing knowledge that's within those attention weights.
Right on. And then they fine-tune the entire model using a special kind of loss function called reverse KL divergence. This basically encourages the student model to really closely mimic the teacher model's most confident predictions.
So it's like saying, hey, focus on the areas where the teacher is absolutely sure.
Exactly. And of course, none of this distillation magic would be possible without a really well-crafted data set. For Mamba, they actually used a combo of 2 datasets, FineMath 4+ and OpenMath Instruct 2, and that gave them a whopping 8 billion tokens to work with.
Wow, that's a lot of data.
Yeah, and then for Mamba and Llama, they just focused on the OpenMath Instruct 2 dataset, which also had 8 billion tokens. Something interesting is they actually masked the user prompt during training, so they were really focusing the loss computation just on the model's output. So this really highlights how task-specific these models are. They're all about generating those solutions, not just understanding the prompts.
They're laser focused on getting those right answers, which, ties in perfectly with that emphasis on coverage. Now, they didn't just stop at distilling these models. They also looked at whether doing more supervised fine-tuning using that same OpenMath Instruct 2 dataset could squeeze out even more performance.
And the results were really impressive. After just 2 epochs of this fine-tuning, both the Mamba and Llama 1B and 3B models showed really big improvements in both coverage and accuracy. It really shows you how powerful it can be when you combine distillation with that kind of task-specific refinement.
It's like taking an already talented student and then giving them even more personalized coaching to help them really excel.
Yeah, that's a great way to put it.
So we've covered a ton of ground here, from the big picture reasons behind this research to all the details about distillation and fine-tuning. Can you give us a quick recap of the key takeaways from this paper?
For sure. I think the biggest takeaway is that smaller, more efficient models, especially those based on these subquadratic architectures like Mamba, they can be incredibly powerful. You know, they can often match or even beat those big transformer models, especially when time and computing power are limited.
It really changes the way we think about designing and using these large language models, doesn't it?
It totally does. Another key insight is that smaller and larger models have different strengths. Smaller models are great at generating lots of correct answers, showing high coverage, while larger models are usually better at traditional accuracy, meaning they have a higher chance of hitting that right answer on the first try.
So it's not just about going for the biggest, most complex model. It's about choosing the right tool for the job.
Exactly. And lastly, we saw how powerful supervised fine-tuning can be. It can dramatically improve those distilled models, making them even more competitive against those bigger, more resource-hungry transformer models.
So we've established that these distilled models are fast, efficient, and surprisingly accurate. But how do they actually do when we put them to the test on those real-world reasoning tasks? To figure that out, the researchers looked at 2 main things, coverage and accuracy. Can you walk us through those?
Yeah, so coverage basically measures how good a model is at finding the right answer at least once within a certain number of tries. And it's super relevant for tasks where it's easy to check if a solution is valid, like in coding or writing proofs where there's a clear right or wrong answer.
Right, it's like not just finding a needle in a haystack, but knowing that the model is capable of finding that needle, even if it takes a couple of tries to get there.
Exactly.
Right.
And then you've got accuracy, which we've talked about before. It focuses on how often a model gets it right on the first shot.
Got it. So accuracy is all about precision and being consistent.
Right. And to measure accuracy, they used a couple of different strategies. One is majority voting, which basically means you look at multiple answers the model generates and you pick the one that pops up the most. It's like getting a bunch of experts together and going with the most popular opinion.
That makes sense. And then there's weighted best of n, right?
Yep. Weighted best of n is a bit more sophisticated. They use a separate reward model to go through each answer the model generated and give it a score. Then the one with the highest score is the winner. It's kind of like having a panel of judges rank each solution and pick the best one.
So it's not just about how often an answer appears, but how good it is according to another AI.
Exactly. Now let's dive into the results. When it came to coverage, those distilled models were rock stars. They consistently hit the same coverage levels as the big transformer models, but they did it way faster.
There's that speed advantage again. It's like they're able to explore so much more in the same amount of time.
And when you factor in time budgets, those faster generation speeds really gave them a leg up. Because they could crank out so many more solutions, the distilled models often outperformed those transformers when it came to accuracy, especially when time was tight.
So in a real-world setting where you don't have forever to wait, these smaller models could actually be better problem solvers.
Yeah, for sure. Another interesting thing they found was how model size plays into this whole coverage versus accuracy thing. Smaller models seem to be better at coverage, while bigger models usually do better on those classic accuracy metrics.
It's really important to think about what you need from a model. Do you need it to come up with a ton of potential solutions, or do you need it to nail it on the first try?
That's the question. Now, remember supervised fine-tuning, or SFT, that we talked about earlier? Well, the researchers took it a step further and looked at what would happen if they did even more SFT after the distillation process.
And what happened? Did they see any more improvements?
Oh yeah, the results were really promising, especially for those Mamba Llama models. Both their coverage and accuracy got a nice boost after that extra round of fine-tuning. They really solidified themselves as strong contenders against those bigger transformer models.
It's like taking a student who's already super talented and giving them that extra push to really refine their skills.
I like that analogy. So to sum it all up, this research really flips the script on the idea that bigger is always better when it comes to language models.
Totally.
It shows just how powerful those smaller, more efficient models can be, especially when time and computing power are limited.
Absolutely. And it also highlights how important it is to really understand what you need from a model.
Yeah.
Do you need high coverage, high accuracy, or a bit of both? Figuring that out is key to finding the best approach.
Couldn't have said it better myself. And who knows what other exciting discoveries are waiting for us as research in this area keeps moving forward. It's a really cool time to be working in AI.
That's for sure.
Yeah.
There's so much room for new ideas and progress in this field. Well, that wraps up our deep dive into thinking slow, fast. We hope you enjoyed exploring this world of distilled language models with us. Until next time, keep those AI engines humming.